Today we're going to be talking about Stratify 2.0, which is a product that is on the market. It's been on the market for several years. PHI has continued to update that with new features and making some modifications, improvements to the product over that time. A brief outline of today's talk. We'll do a brief introduction of Angle Resolved XPS. We'll be calling that ARXPS, and the software that we're using to do the analysis of ARXPS data, which is Stratify. Then we'll move on to talking to some examples of using Stratify. And then we'll cover the new GUI for the software, the graphical user interface. Very, very simple to use and very efficient at processing data. Then we'll introduce several new features as well, including the combined aluminum and chromium X-ray beams for analysis. So I'll expand on why we're using both of those beams later on in the presentation. We'll also cover fractional coverage analysis as well during the course of today's talk. So we'll start off with an introduction to Angle Resolved XPS. In the sample, you would have X-ray beams coming into the sample, and it'll generate photoelectrons. Will then traverse through the material to the surface, and how far it travels it depends on the IMFP, the inelastic mean free path, which is the distance that the electron travels prior to losing its energy by collision. It depends on the material itself as well as the kinetic energy of the electron. The kinetic energy of the electron depends on the X-ray beam itself. The higher the X-ray beam energy, the increase in kinetic energy. Here we have an image called the universal curve, and this shows the typical relationship between kinetic energy of the electron and the IMFP. In general, when you have a larger IMFP, you would typically see in XPS and HAXPES, you would have an increase in the IMFP because of the higher kinetic energy. There's a basic relationship in the equation at the bottom. You'll see lambda representing the IMFP, and you have a dependency on the Z in the atomic number Z, as well as the kinetic energy. There are multiple different equations, theoretical and experimental. We'll talk a bit more about that in the presentation as well. So in typical XPS experiments, you would have a sample not tilted. In that specific situation with the arrow pointing upwards here, you would see you have a 90-degree angle, which means that which is the takeoff angle to the detector. As you tilt the sample, the detector is not moved. It is in a fixed position within the XPS instrumentation. And by tilting the sample, you change the takeoff angle. So here we can see we're at 30 degrees. And we do that because it allows us to change the information of the actual depth of the sample. And I'll give you another example here as we progress through this slide. This specific example of silica on a silicon substrate, you can see that we have different curves. Each represents a different takeoff angle. From 20 degrees ranging to 75 degrees. Here we can see two peaks. The one on the left is a silicon oxide peak, which represents silicon oxide. On the right, it represents the substrate, which is elemental silicon. So as you tilt the sample to, say, 20 degrees, you will see that overlayer becomes more sensitive to the detector. So now we're going to talk about how we typically would model the intensity as a function of the takeoff angle. So for example, with IMFP, of the generated photoelectron, this basic equation represents that. It's in the form of an integral. The problem with this equation, though, is it's very difficult to calculate computationally. Rather difficult to do that. So our approach, using Stratify, we use the forward calculation. And we do that by using the direct line approximation, SLA, which really means, if you look at the image on the right, the blue arrow represents the path to the detector. So within Stratify, we assume the electron will traverse in a straight line to the detector without any scattering taking place, such as the elastic scattering. We're assuming that is not taking place. Basically how Stratify is able to do its calculations. So I'm going to show you a step-by-step process of how we arrive at our results. Basically, it's 4 steps. You first start off with the software. Within Stratify, you would then input what you know about the sample, including layers and approximate thicknesses, as well as the XPS transitions that you're collecting, and then assigning to each of those individual layers, to the best of your ability, of course. At that point, you would hit the fit button, and then Stratify in the background would predict the intensity of the spectrum based on the information that you have been put into the software. It will then do a comparison of the predicted intensity against the experimental intensity. If you're off, Stratify will automatically modify the layer thicknesses to minimize that deviation. After finding the best fit, it will then output the results. So I want to circle back to finding the best fit and what that means. The plots that you see here in this slide represent the heart of Stratify, if you will, of that analysis. If you look towards the left, it shows the entire intensity of the different species in the sample of Hafnia on silica on a silicon substrate. And so this shows the normalized intensity. If you were to look closer into more detail here, you would see a dotted line, which represents the what Stratify is predicting as the intensity. The solid line is the actual experimental intensity. So the intention of Stratify is to try to minimize the difference between those two. And that is quantified by goodness of fit, which we consider chi-square, you'll see in the bottom of the equation. We also use a variance, and we do that by approximating the peak area to assume that variance. So now I wanted to cover a few examples of Stratify. One very nice thing about Stratify is that it provides the ability to use a single takeoff angle analysis in lieu of needing to tilt the sample multiple times at multiple angles. So this is a great feature, and I want to show you a comparison of the 2 experiments that we've done. One with 5 different takeoff angles versus the experiment with just a single takeoff angle. The data actually very close to each other, and just shows the ability of Stratify to do those calculations without the need for multiple takeoff angles. Another great example, it's to do with multi-layered films of aluminum on Hafnia on silica on a silicon substrate. In this specific example, we've included oxygen, an oxygen signal within Stratify. If you were to look at the numbers, they are a bit off compared to what we were getting with the TEM, which is transmission electron microscopy, which you'll see on the left. So here we have the concentration of the different layers. Not an exact match with what we were getting within Stratify results, which you'll see on the right-hand side. So what we could do at this point is go ahead and try to remove the effect of oxygen within Stratify. Here you see the numbers have improved a bit by removing oxygen from Stratify. And how that works, I'll talk a bit more about that in a moment. But basically, with every layer, it's going to have oxygen, right? Anion oxygen. So every layer will also have a unique species. Aluminum, hafnium, and silicon. And you can assign specific unique species to each of those individual layers. And that'll give you the thickness of those layers. So compared to what we got with the model with just the cations, again, we are even that much closer in agreement to the values between the table on the left versus the one on the right, the data on the right. And the reason why that happens is if you were to hold that oxygen spectrum, O1s spectrum, you would see a single peak of oxygen for several different takeoff angles. That single peak represents the different species at the same time, from alumina, hafnia, and silica. So it's very, very hard to curve fit in that fashion. So you're able to remove that effect of the oxygen, and that'll give you a more accurate estimate of that film thickness. So let's move on to this new GUI, the improved graphical user interface within Stratify 2.0. This one, though, you'll see the very first thing, this is what you'll see as you load the program initially. You will have an interactive screen with many different plots throughout the screen, as well as inputs and outputs. I'll start off working from the left side, which is one of the first things that you'll see as you load the software. It's the normalized intensity against the different takeoff angles. Earlier, I mentioned the concept of goodness of fit, which is represented by chi-squared. And that shows the number of how close your data is to the actual calculated intensity. On the right, we have a relative depth plot, which is a qualitative measurement of the approximate order of the layers within the sample itself. And how that works is if you look at the y-axis, you'll have a formula there, which is the natural log of the intensity of the species at a smaller takeoff angle, a small takeoff angle. And that's versus the intensity at a large takeoff angle. This is not always accurate in the right order, but it is used to assist the analyst in calculating what the sample might be made of. The small bar represents being close to the surface compared to the large bar, which is deeper into the sample itself. Here you'll see the layer table. These are the layers that you think are in your sample using RDP on the top right. You can estimate the order and then input that data here in this list and the approximate thickness. You can pick which layer to actually fix. Most commonly done is the substrate as fixed, because most times the substrate itself is semi-infinite. So for example, you can set it as 500 nanometers and then allow all the remaining layers to float. So in this table, you'll have different information, including surface coverage of the individual layers, as well as we're introducing this new concept, this new analysis called fractional coverage. So you can check off which layer you'd like to do a calculation of fractional coverage by using this table. After the analysis has been set up, the layers, once you set up the layers in that particular window, you can just assign a different transition to each of those individual layers. So for example, you could say set up a layer as hydrocarbon, and that would represent adventitious contamination layer. And you can assign a carbon transition C1S to that. And then the next layer, you could say, let's say, hafnium. You could assign that next and assign the appropriate hafnium 4F to that individual layer. With silica and with silicon substrate, so on and so forth, you could do the same thing. Earlier, I mentioned the concept of removing the effect of oxygen, and that is done here with the drop-down menu. And you can click on Exclude Anions, as you can see here. There are other options to include anions if it's suitable in that particular situation. We do offer both options. So after establishing those inputs, you then would click on Fit, which is the orange button that you see here. So that will generate output, as you can see. And this shows the approximate thickness of the individual layers in your sample. Also, our software offers different options of IMFP methodologies. Each methodology has a different assumption, a different purpose. Most common method would be TPP2M. So moving on, we have aluminum attenuation length, which is the table that you see here. And that shows the IMFP of each of the electrons in each of those layers. So for example, here we can see the IMFP of silicon 1s in the silica layer, as well as the hafnia layer. And we can also modify that IMFP in the database itself. This represents the icon. You see where my mouse is. That's a specific aluminum attenuation length. If you would like to access that information, you have that ability. So now moving on to the export option that we have. We have the option of exporting all of the plots into PowerPoint, for example, for ease of presentation use, presenting to teams or publications. Also, we have the ability to exporting this information to Excel with tabulated information. And you can also export to a text file, which is great because that allows you to save the depth profile and concentration of the species with respect to the depth. So now I'd like to introduce several new features that have been set up in the toolbar at the top of the screen. So one of the new features that we've implemented is the combination of the chromium and aluminum X-ray data. And that is done in a very, very easy fashion. So first you would just load the file, for example, the aluminum data first. Then you would click on this plus icon that you see right here. By clicking that, it will incorporate that data to your aluminum data, the chromium data to your aluminum data. Also, we introduced a new flexible MAT-SIS, and that MAT-SIS is basically a system of your sample structure. So if the analyst is setting up structure and you want to apply that to your next sample without having to re-input all of the information all over again, you could use that feature to just save the information for a subsequent file and go ahead and load that. And that, of course, would save that sample structure for you. Another new feature is simulation mode. Let's say the analyst wants to run angle resolve XPS, but you don't know exactly what the transitions to be used are. You can click on this button prior to starting the experiment, and you can input information. The system will then give you the best transition to collect within your experiment. Also, we have a batch processing ability or functionality. If you have, say, dozens of data files, you can set up your system, your layered system, click on batch processing, and that will process everything for you with just the click of one button, and then output all the results into a spreadsheet, for example. We also have functionality for other options, analyzing options. So with bulk or with ultra thin film concentrations, you have this option. So if the film itself is, the layer becomes, as it becomes smaller and smaller, the concentration could change. You can also instruct the software to use either ultra thin film concentration or a bulk concentration. And those numbers can be changed within the database itself, within Stratify. So just summarizing what's new in the GUI. That is a summary of what's new in the GUI. Moving on now to simulation mode. So with simulation mode, again, the click of one button that happens, then the user would input the sample structure within the layers table, as you see here. You would incorporate what the film is made of, the thickness you might think it is. Then by clicking this fit button, the output would result in the transition table of different transitions. And that is ordered by the intensity, highest intensity going first from left to right. So for example, with the system of hafnia, on silica, on silicon, the most intense thing you're going to predict is hafnium-4F with aluminum X-ray beam. Then the second most intense item would be hafnium-3D5 using the chromium X-ray beam. If you were to look at the order on the left, as you'll see here, the hafnium-4F does not have a plus symbol next to it, as it does with the second column. That one has that. So the transition without the plus symbol represents the aluminum transition. The transition with the plus sign represents the chromium setting transition, the chromium transition. So with this information, the analyst can decide which transition to collect. And that, again, that order is based on the most intense, deepest layer. So with that information, you can then develop combined aluminum and chromium angle resolved XPS experiment. So let's summarize why you'd want to use a chromium X-ray beam. That depth information depends on, again, the IMFP of the electron, and the IMFP depends on the X-ray beam itself. Now, within HAXPES, it's very difficult. With the X-ray XPS, right? You have an X-ray of a higher energy, which means you have a higher kinetic energy, which thus means you have a larger IMFP compared to the aluminum X-ray beam. If you see the image on the right, you'll see the comparison of silicon 2p photoelectrons generated by both aluminum and chromium X-ray beams. And with the aluminum X-ray beam, the depth where you have 10% probability of an escape at the surface is about 7 nanometers for aluminum X-ray beam. Compare that with the chromium X-ray generated photoelectron, you'll have an escape probability of 10% from the depth of 22 nanometers. So the IMFP for aluminum-based transitions ranges from 0.5 nanometers to 4 nanometers, whereas the chromium, you'll see an increase of between 1.5 and 12 nanometers. So now let's take a look at the sample of the 8 nanometers of hafnium on 8 nanometers of silica sample on a silicon substrate. We'll start off with using the aluminum X-ray beam. We'll collect the hafnium 4F and the silicon 2P spectrum, and you'll see here that the signal intensity of the hafnium, as predicted by the simulated results, the intensity, it creates a great spectrum there. But with silicon 2P, there's a lot of noise in the spectrum there, right? We're only seeing a silica signal at approximately 102 eV. But we cannot see the silicon substrate itself. So if we were to use the chromium X-ray beam, now you can see the silicon substrate, which is represented by the second peak on the right. So let's say we're collecting hafnium-based signal with the chromium X-ray beam. You're still not seeing the intensity as you would with the aluminum. If you were to look at the graph on the right, for the same transition of hafnium 4F, you will see the aluminum-based photoelectron generates a lot of signal compared to the chromium-based electron. If we were to try to find an even better chromium-based transition for hafnium, there would be an improvement in the signal with the hafnium 3D5. But the problem here is that the signal is not as strong as it was with the signal you were getting with the aluminum X-ray beam. Even with the larger IMFP, you can see here, with the chromium-based hafnium 3D5. And the reason for that is that the cross-section probability of the hafnium with the chromium X-ray beam compared to the aluminum X-ray beam, it's smaller, right? So the results would suggest then that we could use a combination of the best data, right? That's hafnium with the aluminum X-ray beam, as well as the chromium X-ray beam for silicon. And I'll show you how we combine that on the following slide. So in this experiment, same sample, 8 nanometers hafnia on 8 nanometers of silica. We have 2 experiments. The first experiment being a quick collection of the silica signal, Si1S. The results here have a low signal to noise ratio of 21. You can see in the previous slide where you saw that noise spectra for silicon 1S. So again, with the hafnium, we have a higher signal to noise ratio. So let's say then that we'd run an experiment again with a longer acquisition time to improve the signal to noise ratio. And that brings it up to 209. So we have an improved thickness measurement of each of the individual layers for both hafnia and silica layers. So we have the data uncertainty of the thickness measurements for each of those individual layers, and that is based on the sensitivity of chi-squared to the layer's thickness within StrataPHI, those calculations. So, for example, if the StrataPHI software modifies those layered thickness in the software, those changes are a lot, but the chi-squared does not change as much. That means it's not being very sensitive. So that means it's a higher uncertainty. You'll see the image on the right here, which represents the thickness of each of the individual layers and which transitions we use for those individual layers. The first layer, hafnia, is aluminum-based X-ray. The second layer is silica, which used a chromium X-ray beam. So now let's move on to talking about the second new feature within StrataPHI, which is fractional coverage analysis. So here on the right, you'll see an optical image of a sample of flakes of molybdenum disulfide. And again, that's on a silicon substrate. And those images are stitched together using a digital microscope. Here we used XPS as well as low energy ion scattering, LICE. And we did that to study the fractional coverage. Here you'll see a yellow square, which represents the area that we selected in using LICE, low electron ion scattering, to acquire that data, whereas the black square, the black rectangle, pardon me, represents the area where we acquired the data in XPS for statistical averaging. So in this experiment, we used AR-XPS of each point and then compared that with the LICE results using a dedicated LICE instrument. So here you'll see the molybdenum disulfide flakes. The density has changed as you go from left to right. It might be difficult to see in this particular image here, but on the left, you'll have a lower intensity where that intensity increases as you move right in those flakes. This spectrum shows the results of the XPS experiment on the moly disulfide. And it shows several different peaks, as you can see here, which has contributions from sulfur, sulfur S2S, and then moly disulfide, as well as the moly oxide. So which means we need to do some curve fitting here to separate those contributions. Now, StrataPHI's fractional coverage analysis, we would add them together, the moly oxide and moly disulfide, because those are part of the structure of the flakes. Here we're showing the results of that fractional coverage analysis. As I mentioned earlier, in talking about StrataPHI 2.0, the new GUI, with the click of one button, you can do fractional coverage analysis, and that will generate that value, the fractional coverage value, in the depth profile. And that's going to be in red on the right-hand side of this particular slide. You'll see 65%, which corresponds to the area with 65% on the left. So if you were to repeat these calculations for all 6 areas, you would get a number of 40%, all these different numbers, 40, 42, 41, so on and so forth. This shows very good agreement between the LICE results. And again, the LICE results were 49%, whereas the average of the 6 areas using XPS was 52%. Again, very good agreement. Just to summarize the results of the LICE that was used, in the experiment, we used a dedicated LICE instrument. In that experiment, the sample was irradiated by a beam of helium ions. They interact with the sample and then scatter. So we use that information from the scattering event to calculate the composition of the surface. So for example, the portion of silicon versus moly, as shown here at the bottom of the graph. And how we do that calculation is the area coverage percentage using LICE. We have a standard sample of 100% coverage, moly disulfide, molybdenum disulfide sample. We have 100% coverage on that, and we refer to the calculations of the fractional coverage of the actual tested samples. And I'll show you that, as you can see here, the formula is at the bottom of the slide. So in this experiment, the sample was treated with thermal ions. I'm sorry, pardon me. thermal oxygen. And the reason why we do that, that is done to remove the surface hydrocarbons that have adhered to that surface of the sample. The downside to using that approach is those will convert the moly disulfide to moly oxide. So that means then that it is difficult to use the sample for any subsequent experiments on other instrumentation. So the information with regard to that moly disulfide would be lost by treating it in that fashion. The image you see here on the left is a zoomed-in view using an optical microscope of the flakes of moly disulfide on a silicon substrate. Again, this gives you a better idea of the squared nature of the flakes, or the nature of the flakes. Again, I want to emphasize the results of the Stratify fractional coverage analysis is consistent with what we're seeing in those results in lice. So very good agreement between those two. One of the great things about Stratify, the calculations also incorporate the layers, the thickness layers, as well as the fractional coverage, which is something that lice is unable to do. Lice can only give you fractional coverage. And again, with lice, that requires the sample to be pre-treated. Again, as I mentioned, using that thermal oxygen atoms to treat it. So in summary of the results that we've achieved here, we have several new features within Stratify. We have combined XPS and HAXPES within the same sample, right, to enhance the signal of the depth in the layers, which is typically difficult to see, for example, with just aluminum X-ray beams. Secondly, another new feature was that simulation mode, which assists the analysts in setting up experiments before actually running them. And then thirdly, we have the ability to calculate that fractional coverage of, for example, islands of materials on a particular substrate. Again, showing great agreement between the lice results and Stratify. Also, we have a 90-day trial version of the software for free that's available. Feel free to reach out to us at the email you see here to get a copy of that free trial. Thank you so much for listening to today's presentation.